Hello everyone. In this video I'm going to be continuing the reactions that I left off at last time, and these will be for exam 3 and the final, and these will be very important for those two exams. So last time I stopped off at the formation of primary and using primary and secondary amines to form the imine and the enamine. And now I'm going to pick up at the bottom of page 8 on the reaction sheet, and we're going to be doing the acetyl formations protected carbonyls. And essentially, these two reactions do the exact same thing. All right, they look a little bit different, but if you notice, they're very similar. And what they do essentially is they protect aldehydes and ketones with higher priority for aldehydes over ketones because aldehydes are more reactive, which the description says, and essentially makes them immune to any kind of strong nucleophilic attack. And so it protects the carbonyl and then allows us to do something with the molecule, either turn it into a Grignard or attack what they have over here, for example. They show you the full steps. So they have a carbonyl, they have a ketone, and they have an aldehyde. They use the protection, and then it protects the aldehyde. And then we do a Grignard reagent attack. And so the Grignard attacks right here. And then once we add H3O+, that protonates the O- that forms, and it also removes the acetyl protecting group. So what you need to know about these reactions is that you need the protecting group, whether it's this, whatever, I think it's called the vicinal diol, or you use the 2-ETOH. Either or is fine. This is actually the more common one where you just use this this vicinal ethanol and H+. Okay, so this plus H+ adds the protecting group to the more reactive carbonyl, the ketone or the aldehyde, and it's always going to be the aldehyde. And then to reverse it, to remove it, you always have to add H3O+. So in non-aqueous conditions is how we get it to react, and then aqueous conditions is how we remove it. And so the mechanism is not highly important for this reaction, but many of the reactions have a very similar mechanism to everything that we've done. Actually, if you watch the formation of imines and enamines, that reaction setup is very similar to almost all these new reactions. They're not that hard really. So just to save time, so I can get through a lot of stuff. I don't think you're gonna have to know. I guess let me just show you. All right. So like with every reaction that we see H+, the function of H+ here is to activate the carbonyl. So what's going to happen first is the carbonyl oxygen is going to use one of its lone pairs to abstract a proton, right? So we're doing this in an acidic, non-aqueous environment. And what that's going to do, all right? So we're going to get this positive charge, right? And now the oxygen's positive. Now we're going to increase the dipole moment, and we can actually have a resonance structure at this point. And we're going to get a much more electrophilic carbonyl carbon. And so at this point, something that is not normally strong enough to attack that carbonyl can. So we have an alcohol, right? And so this is going to come and attack, right? And this is going to bump this up. And when that happens, right, so you get this OH, right? And then now we have this oxygen here, right? This has its own hydrogen, and this becomes positive, and then it's attached to this structure, all right? And so now what happens is, I'm going to kind of go all over the place. So now we want this group to leave essentially, and we want this group to attach. So the way that we do that, first step is we're going to go make everything neutral, right? So I need to get rid of this. This is acidic, and so now this is going to be removed, right? So we can remove this usually using, this just says -H. we could remove this using H2O. So H2O is present, even though we said it's not an aqueous, but once the reaction starts, we do, there is going to be some small amount of water, but overwhelmingly it's not aqueous, for the most of this reaction. And so, we're going to get this structure. Oops, right? All right, so now we have that. Now the next step is going to be a protonation step. So now we want to get rid of this group, so we're going to protonate it. And so this is going to become H2O. All right, so it's going to abstract the proton. We're going to have, this guy is here. I'm going to draw it funky like this for now. All right, so we have this right now. And so now this is a good leaving group. What's going to happen is you're going to have this oxygen donate a pair of lone pairs inwards, and this is going to get kicked off. So now this group is gone, and now I have this O, okay, which is attached to another OH group. And so when we do this, this oxygen is now positive, right? And we have another resonance structure. And just like before, the very first step, we have created an activated oxygen, a carbonyl structure. And so now we have another alcohol group that's present. And so this whole process is going to repeat itself. So this is going to come and attack. And then when that comes and attacks, right, this is going to go up. And so now I have this essentially. And now this oxygen has a positive charge. And then all that remains to do is to deprotonate this, and then we get our protecting group. Okay, so not that bad of a mechanism. So just protonation to make something leave, deprotonate to make something stay, so on and so forth. And then, of course, let's say I remove. So this is our final product. Now to remove it, why does H3O plus make this go away, and how do we get this back? Well, it's basically the reverse mechanism, right? So this one of these gets protonated, okay? So we're going to increase the acidity. One of these gets protonated, right? And so this becomes a good leaving group, and that therefore this carbon right here, becomes a accepting group for, H2O. H2O will come and attack. This will get kicked off, right? And then, you have the alcohol part over here, you have the H2O part. Then the H2O will be deprotonated, we'll get an OH group. And then what will happen next? Well, this group, this oxygen will get protonated. And then we'll have another good leaving group, and then the now the OH on the molecule will donate a pair of electrons, and then we'll get a carbonyl-like structure, and then this will leave, and then we'll be at this step. And then you deprotonate and you get back the carbonyl. So the reverse is just basically just doing these steps in reverse a little bit. Okay, so if you understand how it works, and if you understand how something can come and add, and how the function of protonating something to make it a leaving group works, you should do fine on this next exam, because the majority of all these reaction mechanisms have to do with this very same, mechanism. All right, so now I'm just gonna go over the reaction sheet, because I'm not gonna show everything, Okay, so this is just turning, types of alcohols into, switching an OH with a chlorine. So SOCO2 is how we convert a carboxylic acid into a, acid halide, or in this case, a particular acid chloride. You can also use COCl2. More commonly than not, use SOCl2. This is an old reaction that you should know, using a LiAlH4 on a ketone. This is an old reaction that you should know, right? Any nickel, it turns this into an alcohol and takes away all double bonds, triple bonds, all that stuff. This is repeat, right? A primary amine. And here they're just showing different types of primary amines that you can use. So a primary amine is any NH2 connected to some other group. So this is the NH2 that we're using. This is the group. This is like the R group, quote unquote. So this is the R group, quote unquote. This is the, the group. This is the group, all right? This one is used in Wolff-Kirchner, actually. Secondary amines are repeating it. Okay, and now we have some things you have to memorize. So oxidation of aldehydes, and we're looking at a specific type of aldehyde oxidation. So other types of strong oxidizers work, right? But these two in particular only and specifically target the aldehyde. So KMNO4 and chromate and whatever reagents, they oxidize everything, right? But the silver reagents, right, they only oxidize the aldehyde. And so you need to know that specifically, that they target aldehydes. This one you should know already, using the Grignard as a way to attack CO2 and to add a carboxylic acid group once you do H2O+. So this one should be fairly easy and simple to see. All right, this is something that we kind of have done already. I think in a previous video I showed it with a Grignard, and it works the same exact way, except we're using H2O+. So, by the way, if you guys don't understand something or you want, to see the mechanism, find a way to message me. I think, contacting me should be fairly simple. So I can put my UH email or something. But anyways, using nitriles and H2O+ and heat will convert this carbon into the carboxylic acid carbon. So it should really have an R group here, but this is going to make this into the carbonyl and the OH coming off of this. And since it's acidic conditions, the end product is protonated. In basic conditions, the end product is not protonated. So you need to be careful of that. All right. Now, ester formation. So esters. So we're just gonna go through all this stuff. So on the top of there's a ranking for reactivity. Okay, and on the very top of this reactivity ranking, you have these acid halides. Acid halides are the most reactive form of a carbonyl structure. And because of that, they don't require H+ to activate the carbon. They don't need anything. They can form any kind of functional group. As long as you start from an acid chloride or acid bromide or whatever acid halide of any kind, there's only two kinds you're going to use, bromide and chloride. And as long as you use one of those, you'll be able to form any kind of functional group. And so as such, you start with an acid chloride in this case, and we use an alcohol, we're going to form an ester, because the alcohol is now, our electrophile is so good that anything can attack it. So acid chloride plus alcohol gives us this oxygen and this R group coming to this oxygen attacking, right? This alcohol is now strong enough to attack. Same thing would apply with H2O or any kind of thing. And we're going to look at some of these reactions here. So the same thing applies with any kind of amine. So this is a, this amine right here has no R groups. This amine here has one R group. This one has two R groups. And so this forms a primary amide, secondary amide, tertiary amide. So we can use, this is just demonstrating that with an acid chloride, you can really form any kind of functional group. Here we have an old reaction that you should know already, Fischer Esterification, so carboxylic acid plus an alcohol in the presence of H+. This is not step 2. This should be with it, not, this is one step. And small changes are required. So you form the ester. Okay. This is the diazomethane reaction. That's another way of forming an ester, but specifically an ester where this is the R group. So you cannot form other types. It will only allow you to add a CH3 group. And the mechanism is not, I don't think it's important for this right here, but it is interesting if you want to see it. I'm not going to show it right now because to go over a lot of reactions. Direct amide synthesis, so we have a carboxylic acid and we have a primary amine, and I believe it's totally acceptable for you to form the amide without the presence of H plus. So no H plus and just adding a primary amine, you can form an amide. Here we have some reactions, right, using the LiAlH4. And so LiAlH4 in the presence of any of these things will be reduced completely. So we have a ketone. This turns it into alcohol. We have a carboxylic acid that turns it into an alcohol. We have an amide. Amide is the only one where you don't form an alcohol, actually. So the carbonyl, this oxygen is completely removed, and you get CH2 and H2. Then we have a nitrile, and this becomes, everything here becomes completely reduced. So the carbon gets protons, and the nitrogen will also get protons. So just know that specifically, whenever you have a amide and you have the LiAlH4, it does not form an alcohol. It forms the amine. Okay, this is an amine. All right. All right. The next reaction is diborane reduction, and so this reaction specifically targets the carboxylic acid and does not reduce anything else. So we have a carboxylic acid using B2H6 diglyme, then H0+, will allow us to turn the carboxylic acid into an alcohol group without affecting ketones, aldehydes, nitriles, amides, so on and so forth. This next reaction is just another one that you have to memorize. So you need to know that this causes this complete CO2 group, essentially. This carbon with its two oxygens are completely removed from the compound, from the molecule, and we have it replaced with a bromine group. So this is completely cut off, and then we get a direct bond to a bromine. This next reaction is one that I told you, right? So we have a acid halide. I said that these are extremely reactive and they can react with anything. So therefore, using H2O will give us this oxygen coming and attacking, and we therefore get the carboxylic acid, right? Same thing applies with this new structure that you guys don't know. It's a new one called the anahydride, which is essentially a carbonyl oxygen carbonyl. So just like everything else, this is more reactive than the anahydride, so therefore I can go down the ladder, but I cannot go up the ladder easily. So I can react with a deprotonated carboxylic acid. This is all this is. This is a deprotonated carboxylic acid. And so I can react that, and we know how to get that, right? So you form a carboxylic acid from Jones or whatever, use Na plus on it, right, to deprotonate it. No, actually, don't use Na plus. Use NaOH, right? Using NaOH on a carboxylic acid will give you good yield of the carboxylate, and the carboxylate will come and attack the acid chloride, and this will give you the attachment of this group. All right. This is the formation of a cyclic anahydride. So we have two carboxylic acids on one chain like this, and heat will cause this to come, and this one will come and attack right here, kick this up, and then it'll come back down, and it'll get kicked off, and we'll form the anahydride structure. This is a reaction that kind of fits in later, but what you need to know, it'll be explained later, and it'll make more sense later, but what you need to know for the alpha halogenations of a ketone is that it will basically brominate the alpha position, which is the position that is one carbon away from the carbonyl. So this will add a bromine right here. right? And it's going to be the most sub position because what I believe happens is you form well, here they say most sub alkene major. So I guess the intermediate here is a double bond that forms at some point, which it does because we'll have resonance structure. But yeah, double bond formation, and that's why the most sub is preferred because it allows us to form the more substituted double bond. All right, moving on. This reaction will allow us. So the first step actually will allow you to brominate and replace this OH group with a bromine, and will also brominate this alpha position. Okay. Then we use H2O, and since we just formed, right, so it'll turn this into a bromine, and it'll also add a bromine right here. That's what the first step does. PBr3, Br2. And then because we just formed an acid halide, right, and I said that these are reactive, so in the presence of H2O, H2O is going to form a carboxylic acid. And so that's how you would get a alpha brominated carboxylic acid. All right?